So, hello everyone, welcome back to the course on architectural design of ICs. So, in the last class we are seeing the architecture for this running average circuit. So, we have discussed what is running average circuit. Okay, first we have started with what is average circuit, then what is the meaning of running average circuit, then what is the parallel implementation of running average circuit, then what will be the computation time if I do the hardware for that, then what will be the computation time it requires considering a that means fixed set of number of samples, and then what will be the hardware requirement for that particular circuit also we have seen or we have discussed. Okay. So, and at the end of that lecture we have said that okay, now next we will follow or we will try to find out is there any alternate architecture. Okay. Then if I find any alternate architecture, so at that time what will be the advantage and disadvantage of that. Okay. So, if I just again go back to the corresponding circuit. So, in the last class what we have seen, we have to find out this running average of this x7, x6, x5, x4, x3, x2, x1 plus x0 divided by 8. And what I said that the number of whenever running average means the numbers are coming like x0, then x1, x2, x3, x4, x5, so dot up to x n, the values are coming, where n is the number of samples I consider. Okay. And they are coming in this manner. So, now actually that is in the last class we have discussed that is this parallel architecture. Okay. So, that means as I am having this 8 numbers I have to add. So, we require 7 number of adders, then I have done that. So, the serial implementation of that, whenever we will do serial implementation, so at that time means what? As this particular operation they are being common to each of this. So, that means as this operators is common, so can I use this operators for performing the whole operation? So, that means only one operators will be there, and this will be, that means the corresponding number of samples they will be time multiplexed. Okay. So, here what we are doing parallel implementation means all the samples I am putting to the corresponding particular circuit. Okay. So, whenever I am putting 8 of these particular numbers to the circuit, so at that time I will get, after sometimes I will get the output, right. But if I just put this, because these operations are similar for each of this case. So, in time multiplex, if I just change the corresponding values of this, that means I am having this particular operation. So, at that time initially it will be x0, x1, then at the next time it will be x2, x3, then x4, x5, x6, x7. So, something like this if I just add, so at that time can I get that? Yes, I can get that, right. So, that architecture is basically nothing but the serial operation. Okay. So, at that time how can I do? That means now what will happen? That means what I need is that I need one addition operation, where each one of the input there of this particular input will come to this, and then again what will be the other input to this particular adder? They will be this is the register. So, this is the that means sum which is again coming to this particular block. That means the output is again in a feedback they are connected to the adder, and what I require? I need one additional, that means output for getting the final output, because what we are doing this in a loop. Okay. And at the final, whenever this circuit will say that okay, the operation is over, or we have seen in that means in the last few classes that whenever we are doing any computation in a loop, so at that time I need one breaking point. That means okay, this is the condition where this loop will be, the execution of the loop will be over and the corresponding results will be gone to the output bus. Okay. So, that means now I need one output enable signal whenever this will indicate that okay, this is the number of, so 1000 number of samples it consumes. Now, you just produce the results to the output. Okay. So, now how can I do that, or how, that means what is the, that means things, that means how this working of this particular circuit. So, initially x0 is coming. So, as this is registered in clear, that means it is cleared initially. So, y x0 will be added with 0 at the very beginning. So, I am getting this is s at this particular point. So, this is at x0. So, then that means now this is x0 is coming over here. Now, next sample is available here. So, now what I am doing, x0 plus x1 I am doing. Okay. So, then what is the output, x1 plus x0. So, now this is available at this particular register, the corresponding value for this x1 plus x0. So, now in the next this x2 is available over here. So, now x2 will be added with what, if this is y1, then it is with y1, that is y2, which is nothing but x2 plus x1 plus x0 equals to y2. Okay. Then again in the next what will happen, next clock phase, clock cycle what will happen, now x3 will be available to this. So, now x3 will be added with y2. Okay. Then x3 plus, that is equals to y3, correct. So, now x3 plus x2 plus x1 plus x0, that is equals to y3. So, something like this, in this manner this that means loop will start counting or start adding in each of the clocks. Okay. So, in this particular case, if I consider, so at that time what will happen? So, that means again to all computing all these particular samples, what I require? I need to wait for 999 second for this, and what I require? I require this one addition operation, and then again what is this 1 nanosecond, right. So, what is the time? That means 1008 nanosecond I require. Okay. So, I think, so here it will not be this will be the total computation time for this, that will be 999 plus 3 into 8 plus 2 into 1. Okay. So, that means this will be 1000 and then this is 25. So, 1025. Okay. So, in the last I think I have mentioned with 1016. So, this is not the correct number. So, 1025 nanosecond is the correct number for that particular circuit. So, here what I am doing, I require only 1008 nanosecond for computation of 1000 number of samples in a serial fashion. So, there what I am getting, there I am getting this y0 and y1, then y2 after 25 nanosecond, sorry 26 nanosecond. Why? Because if I am considering this, so at that time what I require? 1 for this and 24 for this particular stage, after what this is also 1. So, total 2 plus 3 into 8 nanosecond, thereof 20 nanosecond. So, y0, y1, y2, y3, y4, these samples are basically I have got after this 26 nanosecond in each of this case. So, here after that means running all this process, I am getting the corresponding this 1008 nanosecond and then I am getting the corresponding value. Okay. But if I consider this, so at that time the hardware requirement is that hardware cost, what is that? 1 adder and 1 register. So, in the previous case how many I require? There are 7 adders and total 9 registers. So, that means that has been reduced to 1 and 1 over here. Okay. But here what is the problem with this? I have to as I am doing this serially. So, that means the wait time for getting the output, that will be more. Okay. For getting this y0 and y1, so something that will be more. Why more? Because on that particular case, so suppose for this parallel implementation case, whenever I am doing this, so at that time what is there? That means in each of these blocks, whenever I am doing this, so at that time only for this, as this is 8, this is 8, so sorry, okay, there I have considered 5, here I have considered 8, so that is the problem. So, 8, 8, 8 if I consider, okay. So, then for computing of this and this register delays are 1 nanosecond at this stage. So, total 26 nanosecond I require for computation of this particular stage, right. But the thing is that whenever I will just do this serial implementation of that, at the time how many times I require? I have to require here also one register, right. So, now x0, x1, x2, x3 something like this it is coming. So, that means for each of this stage I require total 8 over here and 1 for this particular register. So, 9 nanosecond I require the time requirement for computation of one stage. That means, one of this addition operation it require total 9 nanosecond. So, here how many times? That means, what are the numbers I require? That is up to x7, right. So, that means after 7th cycle I will get the first output which is enabled at this particular point. So, that means total 7 into 9. So, 63 nanoseconds I have to wait for getting the first results. Okay. So, that is why here, and what is the number over here which I require? That is 20 nanosecond, but what is the number here I require? That is 63 nanosecond. Okay. So, that is why here though I can reduce the corresponding hardware, but I have to for each of the samples to be computed, that I require more time to be wait than this particular parallel implementation. Okay. So, this is the advantage. That means, the advantage is that advantage for this serial architecture is that I am getting this area there is lesser, that means the power will be also lesser, but the time is more. Here what is happening? Area is more, power is also I can say that is more, but the time they are less or sorry lesser than this one. Now, my point is that considering these two particular case, this is the parallel, this is the serial implementation. Can I that means design one particular circuit where I can get both the benefit of this two particular circuit? Can I do that? So, if I want to that means now what is my observation point here? That means I will take the advantage of this serial and the advantage of this as the time in a particular circuit. So, for that if I just coming to this, that what I said y 0 equals to what? That is x 7 to up to x 0 divided by 8, correct. Then y 1 what I said, thereof x 8 to x 1 divided by 8. Then what is y 2? That is x 9 to x 2 divided by 8. So, something like this it is happening to y n. Okay. Now, from these two particular equation, from these particular equations, so can I that means make one or can I observe something so that I can do the modification and I can get one better circuit, or what I need to do, that means I need to find out one particular circuit where I can use or where I can get both the benefit of that serial implementation as well as the parallel implementation. So, if I just that means look into these two particular y 0 and y 1. So, at that time you see only the thing is that means it in this particular position x 0 is here and in this case the newer value is the x 8. That means, here it is x 0 which is not common in this particular two case, and x 8 is the another number which is not common in this particular case. Rest of the all values are same in these two equation. So, considering this, can I change this y 1 value something like this? Can I write y 1 equals to y 0 plus x 8 minus x 0 divided by 8? Can I write that? Yes, I can. How I can? Because what is y 0? Y 0 is nothing but x 7 to x 0, right, divided by 8. Then here here what I am doing 8, right. So, now x 0 will be cut. So, it will become x 8 up to x 1 divided by 8. Then again this y 2, can I write that as this y 2 again, that will be written as what? Y 1 plus x 9 minus x 1 divided by 8. Can I write that? Yes, I can. Why? Because this is x 8 to x 1 divided by 8 plus x 9 minus x 1 divided by 8. So, x 1 cut. So, x 9 to x 2, x 9 to x 2 addition divided by 8. So, that is y 2. So, now that means now what I am doing, that means the previous computed values of this particular number samples, they are being used in the computation of the next sample, that means next averaging of this particular circuit. Okay. So, then what will be the circuit or what will be the architecture for this particular equation? Now, if I just generalize this equation, so at that time y n will be what? Y n minus 1 plus x n plus 1 minus, that will be x 0, or that means x, yeah, x 0 if I consider divide by 8. Okay. So, now what I require is that here I require 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, that means what I require is that I need this x 0, x 1, x 2, x 3, x 4, sorry x 4, x 5, x 6, x 7, x 8. I need to do this minus of this particular 2. Okay. This is nothing but one FIFO, that means the first in, first out. Now, next what I have to do? I have to add with the corresponding this y n minus 1. Okay. So, now I need one adder circuit where one of the input will be this and the output will come from, sorry, here one register I need to put. So, this is y n, and as I am putting register, so this is became y n minus 1. Okay. So, and this is the that means the inputs are coming like this x 0, x 1, x 2, x 3, x 4, something like this it is coming. Okay. So, now consider I have one 9 bit of FIFO here over here, and then I have put this 9th bit here and the 0th bit here for doing this subtraction. Then I am putting to a that means adder circuit where the output is that means feedback to with one connected with one register that are connected with this, and this my that means subtractors output, they are connected to the another input of this adder. Now, you that means what is the operation or how this is basically operating for computation of running average circuit. Let us see that. Okay. So, initially what is happening? Initially x 0 is coming. Okay. So, then x 0 will be filled over here and rest will be all zeros, right. So, that means x 0 minus 0. So, x 0 is coming over here, and then this is basically coming to this particular output. So, in the next clock cycle what is happening? So, x 0 is now coming over here, x 1 is changed to this. So, what I said, this is nothing but one FIFO. So, that means x 0 initially was coming to this. In the next clock cycle what will happen? X 1 will be filled over here, x 0 will come to this particular position. So, now x 1 and here it is 0. So, now x 1 this value will be updated with x 1. So, now what will be the output of this? That will be x 1 plus x 0, because x 0 is the another input and x 1 is the other input. So, x 1 and x 0. So, now this value will be updated with x 1. Okay. Then again in the next third sum, that means clock cycle, what will happen? X 2 will come over here, x 1 will be here, x 0 will be here. So, that means now this value will update again with x 2 and initially what was the value? That was x 0 plus x 1. So, it will be x 0 plus x 1 plus x 2 now. So, that means if I consider this, so y 0 value is x 0 at the very beginning, y 1 value is x 0 plus x 1, then y 2 value is x 2 plus x 1 plus x 0, then y 3 value is x 3 plus x 2 plus x 1 plus x 0. So, something like this it will be run. Okay. So, whenever all these values are fixed, that means all full, whenever that means this value is x 8, this is x 0. So, now at that time if I consider this, that means whenever this is x 7 and let us consider this is x 7, this will be 0 up to this is x 0, right. So, now whenever I will consider this x y 7, okay. So, at that time all will be there up to x 0 divided by 8. So, in the next what will happen, this will be filled with x 8 and this will be filled with x 0. Now, in the previous case what we have considered, that is x 8 minus x 0 along with y 0 at that time. So, it is not y 0. So, at that time this is this, y 0 means is nothing but this particular operation. So, y 0 is we are considering, in this case y 0 we are considering this. So, that is why y 0 is written over here. So, here y 7 is that particular case. So, at that time what will happen? So, that means it will be y 8 will be y 7 plus x 8 minus x 0 divided by 8. So, y 7 is nothing but this corresponding value, 8 values we are not considering over here, we are considering only this. So, x 8 minus x 0, this is what, x 7 dot plus x 0 plus x 8 minus x 0. So, x 0 will cut. So, it will be x 8 plus x 7 up to x 1. Now, finally, what I have to do? I have to pass through one this and then the LSB will be cut. So, this is the output enable signal. Okay. So, that means now you see only to fill this particular register I need to wait. After that, in each of these cycles I will get the corresponding output. So, in this particular case what is happening? I have to wait for 63 nanosecond, but in this case I do not have to wait. So, to fill this particular, that means blocks, how much time I require? All this value 9 nanosecond for filling up this 8 values, 8 nanosecond to fill up all these particular cells. Okay. So, then again if I consider this adder and subtractor delays are same. So, at that time 8 nanosecond delay I require for this and 8 nanosecond delay for this and this is for 1 nanosecond. So, the total computation time is now, what is that? The computation time which I require, that are 8 nanosecond over here plus 8 nanosecond over here, then again 8 nanosecond for this particular case and a 1. So, that means total 25 nanosecond I have to wait. And what is the adder? So, that means the hardware cost is 2 adder, if I consider adder and subtractor same, 2 adder and 1 register, total 10 register, I think 10, if I consider each of this cell also one register. So, 10 registers. Okay. So, that means if I just again come back to this, now let us conclude to this. For the parallel implementation, that means the time requirement is how much? 26 nanosecond, and the area is 7 adders plus total 9 register, right. For serial implementation, time is 63 nanosecond and the area is 1 adder and 1 register. For this particular implementation, that means this that means if I consider this as a combined mode. So, at that time the time requirement is how much? 25 nanosecond, area is 2 adders and 9 register. So, that means now you see in this particular case what I said here, I am getting this requirement of the area is advantage over here, but the time requirement is very poor. In this case time requirement, that means the computation time, they are very good, but the area requirement they are very poor. But in this case I can manage, the time is also good, the area is also good. That means both of the advantage of this serial and parallel, they are being used in this particular case to get the corresponding optimized hardware for running average circuit. Okay. So, what we have done, that means now what I am trying to say is that you have to note down, that means what are the advantage or what are the strength of this particular circuit and what are the weakness of this particular circuit or this particular architecture. Then based on that, how we can come to a newer architecture so that I can get more advantage in terms of speed, power, area. Okay. So, we have started from this, that means basic, then we have seen these architectures, and from this architecture how we can build one newer architecture, that we have seen. Okay. So, it is not that this is the final architecture, again people have done that means several works or several researches on finding out the corresponding optimized hardware for running average circuit. So, this is only the one example I am considering. This is not the case that only one example is there, or for this particular case this architecture. There are several type of that means blocks are available, signal processing blocks. So, for each of this case this kind of things happens. Okay. So, that means what will be the best architecture where I can get the performance on the higher side. Okay. So, for that means for today this is it. Again we will start with newer thing on the upcoming classes. Thank you.